Geometrical isomerism. Geometrical isomerism is the configurational isomerism which is due to restricted rotation is said to be geometrical isomerism. Restricted rotation means carbon-carbon single bond rotation is restricted due to carbon-carbon single bond rotation is restricted due to formation of pi bond or due to formation of cycle. Okay, geometrical isomerism expressed in three different prefixes. Geometrical isomers have three different prefixes. Geometrical isomers have three different prefixes. They are: one is cis trans, prefixes cis and trans. Second one is prefix E and Z. Third one is syn anti. Three types of prefixes used to show geometrical isomerism. Okay, so in these examples are geometrical isomerism in alkene. We are going to see geometrical isomerism in alkenes. Geometrical isomerism in alkene, I will write geometrical isomerism in alkenes. Example 1, geometrical isomerism in alkenes. Geometrical isomerism in alkenes. So first topic 1 otherwise anyway, geometrical isomerism in alkenes. Okay, so geometrical isomerism in alkenes. In alkenes there are two types of prefixes. One is cis trans, other is EZ. So first is cis trans notation. First cis and trans prefixes. Cis and trans notation for geometrical isomerism. Whenever we call it cis isomer, geometrical isomer cis, geometrical isomer trans. Cis isomer, trans isomer, both are geometrical isomers only. E isomer, Z isomer, geometrical isomer. Syn isomer, anti isomers, they are geometrical isomer. So cis trans notation. Whenever two similar groups present on same side of carbon-carbon double bond. Same side of carbon-carbon double bond. Carbon-carbon double bond. Whenever similar groups present on same side of carbon-carbon double bond, it is said to be cis isomer. We call it cis isomer. In the similar way, whenever two similar groups present on opposite side of carbon-carbon double bond, it is said to be trans isomer. Very simple. If similar groups present on same side, cis isomer. If similar groups present on opposite side, that is what? Trans isomer. Cis isomer, trans isomer. Okay, take this example for cis trans isomers. Examples for cis trans isomer. If carbon-carbon double bond system is like this. Carbon-carbon double bond A, B and A, A, or otherwise say this is B, B. Here similar groups, BB are similar groups present on same side, or with respect to A also, A are similar groups present on same side. This is what cis. If A group, B group, B group. Here similar groups present on opposite side of carbon-carbon double bond system. We call it trans-isomer. Trans-isomer. With respect to A also, A is also similar group, trans-isomer. If you take only one similar pair, A here, B here, B here, D here. In this case, with respect to B only, we can assign geometrical isomerism. BB groups present on opposite side. So, trans-isomer. With respect to A, is it possible to assign geometrical isomerism? Not possible. A, D are different. Only with respect to B pair, B. If both B are present on same side, like this. This is D and this is B. Here B groups present on same side. B groups present on same side. So this is what? Cis. Okay. So if you take this example, A, B, A. For this cis-trans isomerism possible or not? Geometrical isomerism, cis-trans not possible. Not possible. Why? Here how many similar groups? A. With respect to this one, cis. And with respect to this one, trans. Both are present. So, in this case, geometrical isomerism is not possible. Okay. Next. If you take example, carbon-carbon double bond, here we have methyl group, here we have methyl group, hydrogen here, hydrogen here. See, with respect to hydrogen, two hydrogen same side, or two methyl groups same side. So this is what? Cis hyphen butadiene. Cis butadiene. This is what? Cis butadiene. Okay. If you take this one is hydrogen, other is chlorine. Geometrical isomerism possible or not? Here see, two are different groups. Is geometrical isomerism possible? Yes, possible. With respect to methyl group, similar groups, same side, cis. This is also cis. 2-chloro-butadiene. Thus geometrical isomerism possible. Okay, next. Whenever four different groups are present like this on carbon-carbon double bond system, A here, B here, this is some X group, this is some Y group. Geometrical isomerism possible. Similar groups are there or not? No, there are no similar groups. A, this is X, this is Y. Geometrical isomerism, even though geometrical isomerism is possible, geometrical isomerism is possible. Of course, there are no similar groups on carbon-carbon double bond system, but geometrical isomerism possible. But not cis-trans notation. cis trans notation. What is possible? EZ notation is possible. EZ notation is possible. EZ notation is possible. EZ notation is also called as atomic number ranking method. First take this one. I will give EZ notation, how to assign EZ notation. Okay, take this one. Whenever 4 different groups are present on carbon-carbon double bond, whenever 4 different groups are present on carbon-carbon double bond in alkenes, EZ notation is possible. Instead of cis trans notation, we use EZ. Whenever at least one pair is same on 2 sp2 carbon, if 2 sp2 carbons contain at least one similar pair, cis trans possible. Whenever 4 different are present, cis trans not possible. It is possible to assign EZ prefixes, E and Z prefixes. So what is EZ notation? EZ notation. And when will we use EZ notation? Whenever 4 different groups, 4 different atoms, whenever 4 different atoms or groups present on carbon-carbon double bond in alkenes, we use EZ notation. If all the groups are different, then we use EZ notation. EZ notation is also called as atomic number ranking method. Atomic number ranking method. Atomic number ranking method. What is cis isomer? When similar groups present on same side of carbon-carbon double bond, cis. When similar groups present on opposite side of carbon-carbon double bond, that is trans. Then what is E and Z? So what is E configuration or what is Z configuration? When this is similar to, analogous to cis trans isomerism, when high priority groups or when 2 low priority groups, when 2 high priority groups present on 2 high priority groups or 2 low priority groups, high priority groups. When 2 high priority groups present on 2 sp2 carbons of alkene, it is called, it is which configuration? Same side Z configuration. It is what? Z configuration. It is what? Z configuration. When high priority groups present on 2 sp2 carbons of alkene, same side, when 2 high priority groups present on same side of carbon-carbon double bond, present on same side of carbon-carbon double bond, that is called as Z configuration. If 2 high priority groups present on opposite side present on opposite side of carbon-carbon double bond, that is called as E configuration. E configuration. Z means Jussmann, E means Entagegen. Jussmann, Entagegen. Jussmann means same side, Entagegen means opposite side. See, I will take general example. Here, for example, if you take A, B, X and Y, just example, not atomic number ranking. So in between A and B, B is high priority. Between X and Y, Y is high priority. B, alphabetical, A is 1, B is 2, X is 24 and Y is 25. High priority groups opposite side. This is E, like that. But this is alphabets. A, B, X, Y are alphabet. For atoms, how will we give priority? So whenever two high priority groups, not similar groups, if two similar groups present on same side, that is cis. If two similar groups present on opposite side, that is trans. Whenever similar groups are not present, then we will select two high priority groups based on selection rule. If two high priority groups present on same side, that is Z configuration. If two high priority groups present on opposite side, that is E configuration. Now, how to select high priority groups among four groups, four atoms present on 2sp2 carbon? So that is selection rules. Selection rules for high priority. Selection rule for high priority. Selection rule for high priority. High priority is assigned to atom which has higher atomic number. High priority assigned to atom of high atomic number. For example, see here, I am taking one alkene. Groups are, here group is taking fluorine, chlorine, bromine and iodine. So first on this carbon, one carbon, what is the higher priority? Atomic number of fluorine is 9. For fluorine atomic number 9, chlorine atomic number 17, chlorine atomic number 17, bromine atomic number 35 and iodine atomic number 53. Which one is the high priority group between fluorine and chlorine? Chlorine, high atomic number. High priority is assigned to atom which has higher atomic number, high priority. And between bromine and iodine, bromine 53 atomic number. So what is high priority? High priority group. High priority group, opposite side. So this is which configuration? E configuration. It is not possible to say whether it is cis or trans. High priority groups, not similar groups. High priority groups present on same side, E configuration. If you change their position, here fluorine, chlorine, iodine and bromine. So between iodine and bromine, iodine, between fluorine and chlorine, chlorine is high priority group, same side. So which configuration? Z configuration. Z configuration. So this is first selection. High priority is assigned to atom of higher atomic number. Okay, next take this one. Second one, second selection rule. Whenever isotopes are present on one sp2 carbon, whenever two isotopes, because isotopes have same atomic number, whenever two isotopes are present on same one sp2 carbon, double bonded carbon, then if same, for example like this, here hydrogen is present, here deuterium is present, here chlorine, like this. How will you select? So what is atomic number of hydrogen? Atomic number of hydrogen 1. Atomic number of deuterium is also 1, because both are atoms of hydrogen element atoms. But when you see atomic mass, atomic number is 1. But atomic mass A is different. Atomic mass is, for protium atomic mass 1, for deuterium atomic mass is 2. A is what? Z is atomic number. Atomic numbers. Whenever atomic numbers are same, then verify for atomic mass. A is what? Atomic mass. Atomic mass is equal to number of protons plus neutrons. Okay. A is equal to protons plus neutron. So between A and D, same atomic number, but deuterium is high priority because of high atomic mass. So when atomic numbers are same, high priority given to atom of higher atomic number. When atomic numbers are same, then high priority given to atom of high atomic mass. Whenever atomic numbers are same, we verify for atomic masses. That's my point. Next, third one. When double bonded atoms are present, when double bonded atoms are present, then two of such atoms are considered. Two of such atoms are considered. Two of such atoms are considered. For example, to the double bonded system, if one group is like this, C double bond O, then it is considered as two oxygen atoms for that one, like this. For this, two oxygen atoms, like that. Whenever double bonded atoms are present, oxygen is double bonded atom, then two of such atoms are considered. In the similar way, if triple bonded atoms are present, so take this one. Next, whenever triple bonded atoms are present, then three of such atoms are considered. Whenever triple bonded atoms are present, whenever triple bonded atoms are present, then 3 of such atoms are considered. 3 of such atoms are considered. Okay. For example, if nitrogen is present, like this group is present, is considered as, this is considered as carbon with how many nitrogen? 3 nitrogen. Carbon with 3 nitrogen, like this. Okay. So in this way we select high priority groups and given priority, higher atomic number, next higher atomic mass, then followed by, if double bonded atoms are present, 2 of such atoms considered, and if triple bonded atoms are present, 3 of such atoms are considered. Nitrogen is a triple bonded atom, so 3 of such atoms considered. So after assigning high priority groups, if 2 high priority groups present on same side, we give prefix Z. If 2 high priority groups present on opposite side, we give prefix E. Okay, so in this way EZ configuration, EZ notational system is used for geometrical isomers. EZ isomers, cis trans isomer, syn anti isomer, all are same. Geometrical isomers, EZ, cis trans, syn anti notations are possible due to restricted rotation. Okay, next, how to calculate number of geometrical isomers when more than one double bond is present. When more than one double bond is present, then the number of geometrical isomers, the number of geometrical isomers calculated by following formulae. So now I am going to give some formulas. Those formulas useful to calculate number of geometrical isomers whenever alkene contain more than one double bond. If only one double bond is present, 2 geometrical isomers are possible. Whenever more than one double bond is present, then here 3 conditions. Case 1, if 2 terminal groups or 2 terminal positions are different, then we use one formula, different, then number of geometrical isomers, number of GI geometrical isomers is equal to formula 2 power n. What is n? Where n is equal to number of double bonds. N is what? Number of double bonds. For example, if you see oct 2,5 diene, so CH3 second position double bond CH 1 2 3 4 and CH double bond CH 1 2 3 4 5 6 7 and this is 8. If you see groups here groups are different. This is a methyl group, 2 terminals. After double bond here, this is ethyl group, methyl and ethyl. 2 terminals are different. The number of geometrical isomers are 2 power n. Number of geometrical isomers is equal to 2 power n. 2 power, how many double bonds? 2 double bonds, 2. So therefore 4 geometrical isomers are possible. How many stereocenter? 2 stereocenters. So 4 geometrical isomers are possible. One time we write cis trans here, 1 cis 1 trans. For here also 1 cis 1 trans. Total 4 geometrical isomers are possible. Number of geometrical isomers is equal to 4. Whenever terminal groups are different, whenever terminal groups are same, we use a different formula. Whenever terminal groups are same, take this one. Case 1 completed. We are in the topic calculation of number of geometrical isomers of alkenes containing more than one double bond. In this case 1, when 2 terminal groups are different. Take this one. Next, case 2 is when 2 terminal groups are same. Whenever 2 terminal groups are same. Whenever 2 terminal groups are same, case 2. If 2 terminal groups are same, 2 terminal groups are same, whenever 2 terminal groups are same. Here again, if n is even, then number of geometrical isomers is equal to formula 2 power n minus 1 plus 2 power n minus 2 by 2. 2 power n minus 2, 2 power n minus 2 whole by 2. If n is even, that formula. If n is odd, then number of geometrical isomers is equal to n is odd, then 2 power n minus 1 plus 2 power n minus 1 whole by 2. These are formulas which are used to calculate number of geometrical isomer whenever alkene contain more than one double bond. Here see one example. Hept 2,5 diene. Hept 2,5 diene. So in hept 2,5 diene, CH3, CH double bond CH, CH2, CH double bond CH, CH3. Number of carbon 1, 2, 3, 4, 5, 6, 7. 7 carbon atoms. So hept double bond 1, 2, second carbon 3, 4, 5. Second carbon, fifth carbon, double bond, diene. Okay. So here this is hept 2,5 diene. Terminal groups are same or different? Terminal groups are same. And number of terminal groups same. Terminal groups same. Okay. Next, number of double bonds is equal to 2 and even. So which formula? Geometrical isomers. Number of geometrical isomers is equal to is equals to 2 power n minus 1 plus 2 power n minus 2 by 2. N is equal to 2. Substitute change. 2 power 2 minus 1 plus 2 power 2 minus 2 by 2. 2 power 2 minus 1, 2 power 1 plus 2 power 2 minus 2, 0. 0 by 2, 0. 2 power 0. So 2 power 1 is equal to 2. Something power 0 is equal to 1. How many? 3 geometrical isomers are possible for hept 2,5 diene. In this way we calculate number of geometrical isomers. So geometrical isomers, we have three types of notation: cis-trans notation, EZ notation, other is syn and anti notation. We will see in this video only. So geometrical isomerism in alkenes completed. Next, geometrical isomerism in cycloalkanes. Take this one. Geometrical isomerism in cycloalkanes. Geometrical isomerism in cycloalkanes. Geometrical isomerism in cycloalkanes. Geometrical isomerism in cycloalkanes. See, I am taking cyclopropane. Okay, for this methyl group, here methyl group, we have methyl group here, CH3. Wedge dash notation, this is also CH3, and hydrogen here, hydrogen atom, another hydrogen atom here. So this thick line represents us that atom or group present on the observer towards you. This one present on the board plane, and groups represented with this wedge is backside of the board plane, backside of board plane, and thick line is towards observer, like this. Okay, so two methyl groups towards observer, same side, cis. This is what? Cis. If we take like this thick line, methyl group, and this dash hydrogen here, thick line is hydrogen, and this is methyl. A restricted rotation due to formation of cycle. This bond is not freely rotatable. So methyl group, hydrogen, methyl group, hydrogen cannot be rotated because free rotation not possible through sigma bond, because here cycle formation, the cycle, due to formation of cycle, this bond become rigid, rotation is not possible. Okay, so this is what trans, because methyl group opposite side, or hydrogen opposite side, trans, hydrogen same side, cis. Okay, in this way we assign cis trans isomerism in cycloalkanes. For cyclo, example cyclopropane. In cyclobutane, taking like this, here chlorine, same side, chlorine opposite side. This is cis, this is what? Trans, like that, or at 1,3 position. Cis above the plane, cis One is above the plane, other is below the plane. Trans. So thus geometrical isomerism is possible in cycloalkanes. Okay. Next, in cyclopentane, in cyclohexane also possible. Geometrical isomerism is possible. Next, geometrical isomerism in cycloalkenes. Take this one first. Okay, next, geometrical isomerism in cycloalkenes. Possible or not? We will see here. Geometrical isomerism in cycloalkenes. So it is practically noted that, observed that in cycloalkenes containing greater than 7 carbon atoms only show geometrical isomers. Remember this point. Geometrical isomerism in cycloalkenes containing greater than 7 carbon atoms. 7 carbon atoms in ring only show geometrical isomerism. Which type of cycloalkene? Cycloalkenes containing greater than 7 carbon atom only show geometrical isomerism. For example, for this one, can you say cis? It is looking to be cis, but this is not cis because sp2 carbons, sp2 carbon. For sp2 carbon, what is shape? Trigonal planar. This chlorine present in the same plane. Trigonal planar shape. This chlorine, this ring, all are present on the same plane. In the similar plane, this is also present. sp2 carbon trigonal planar or not? Trigonal planar. Planar means all the atoms around sp2 carbon present on the same plane. Trigonal planar. So this one present in the same plane. All are same plane. Then how can you say two chlorines present same side, two are opposite side? All are same in the same plane. So geometrical isomerism not possible. sp2 carbon, this is sp2 carbon, which hybridization? sp2 carbon, which shape? Trigonal planar arrangement. Even cyclobutane not possible. Gi, geometrical isomerism not possible. Geometrical isomerism not possible. If you take, there are no hydrogen, double bond. Okay, there are no hydrogen. If you take cyclooctane, example cyclooctane, geometrical isomerism possible. See, cyclooctane, how many carbon atom? 1, 2, 3, 4, 5, 6, 7, 8. Cyclooctane. Cis, cyclooctane. So here this become out of plane. Due to steric hindrance, ring strain. Bayer's ring strain theory said that cyclooctanes have high ring strain, so it is bent like this. So what is other possibility? Other possibility is like this. Trans. Trans-cyclooctene. Trans-cyclooctene. Cis and trans both are possible. See this, a double bonded system. Here CH, here CH2. This one, opposite side. This one, same side. Cis, opposite side, trans. Thus, cycloalkenes containing greater than 7 carbon atoms in ring only show geometrical isomerism. Okay, so based on this concept, I will give some example. Take this one. Some examples I am going to give. For this molecule, geometrical isomerism is possible or not? See this alkene, cycloalkene containing 6 carbon atom. 1, 2, 3, 4, 5, 6 carbon atom. Geometrical isomerism. 6 carbon atom with double bond. Cycloalkenes, previous rule, cycloalkenes containing greater than 7 carbon atoms only show geometrical isomerism. Here only 6 carbon atom. Here ring contain only 6 carbon atom. Ring contain only 6 carbon atom. Even though geometrical isomerism is possible. Geometrical, how it is possible? How is it possible? Cycloalkene containing less than 7 carbon atom. How is geometrical isomerism possible? So here geometrical isomerism is not due to not on account of cycloalkene character, but due to cycloalkane character. Cycloalkane character. Is it cycloalkene? This is cycloalkane. How it will become cycloalkane? See this. So this is which carbon? sp2 planar. But if you see this is what? sp3 carbon. One hydrogen, other is methyl. This is sp3 or not? 1 bond, 2 bond, 3 bond. Other is what? Hydrogen. Here other is what? Hydrogen. Okay. So hydrogen means sp total 1, 2, 3, 4 sigma. 4 sigma means what? sp3. sp3 means not planar. Not planar means one of the methyl may be out of the plane like this. So like this. Above, hydrogens are below. Cis trans possible or not? Yes, possible. Cycloalkane character. Forget about this. So this is cycloalkane or not? Yes, cycloalkane. On account of cycloalkane, this molecule shows geometrical isomerism. Okay. If you write like this, example 1, example 2, for this molecule, geometrical isomerism possible or not? Not possible. It is cycloalkane. Cycloalkane or not? Yes, cycloalkane. It is cyclo. Double bonds are not present. All are single bonds. 6 carbon atoms connected by single bond. So cycloalkane. It is cycloalkane. Substituent is methylidine group. Cycloalkane, even though it do not show geometrical isomerism. It do not show geometrical isomerism. This is due to this carbon. So this may be out of above the plane or below the plane, possible. For this one, above the below the plane not possible, because that carbon is what? sp2 carbon. This carbon present on the same plane like this. So same side, you cannot say this. If you write this one up, these two are not same. If you write down also same distance. If you write this one up, same distance on the plane. If you write down also same distance, up also same distance. So geometrical isomerism not possible. Okay, important examples. Next, geometrical isomerism in, take this one. Example 3, last example. 2 more examples we have, but for this one, geometrical isomerism possible or not? Possible, yes. 1, 2, 3, 4, 5, 6, 7, 8. Cyclooctane containing greater than 7 carbon atom. Geometrical isomerism possible on account of this double bond. This is one stereo center. Okay, if you write CH double bond CH2, how many stereo center? Only one stereo center. This double bond is not stereo center, because this is like this. Double bonded carbon, hydrogen, hydrogen. Both are similar groups. So this is not, therefore it is not stereo center, which do not lead to stereoisomerism, geometrical isomerism. Okay, so if you write like this, a double bond here, CH double bond CH3, 2 stereo centers, 1, 2, because so here cyclooctane geometrical isomerism possible, but here CH, and for this what is the other group? Methyl. Different groups are not? Yes. For this carbon, one is hydrogen like this, other is some cyclooctane group. All are different. 2 hydrogen same side. Cis. Possible or not? Yes, possible. If you write different, trans, that become trans. If you write like this, it become trans or not? Yes, trans. It become trans. Thus, this molecule show geometrical isomerism. How many stereo center? 2 stereo center. 4 geometrical isomers possible on account of this one. One is cis, other is trans. Cyclooctane, chair form and boat form. Next, on account of this one, 2 isomer. Total 4 isomers possible. Hope you understood. In this way, geometrical isomerism in cycloalkanes and simple alkenes completed. Next,